All right, so let's do 9-9 and maybe 9-10. This is what I was talking about beginning of chapter 9. Representation of functions by power series. Geometric power series. So basically the idea was if you have a function, you can represent it as a series, which becomes really handy programming. Okay. A lot of the ideas in calculus is built on infinity. But in reality, we hadn't really proved infinity. Something that we assume to be true. Most things in life are discrete. And computer programming and the way they think discretely. They do not have infinite numbers or information stored. There's always finite, right? So during the trig series, we said we can write it as a sum, right? A over 1 minus r, which is equal to a to the r to the n. And we said that this converges when r is less than 1. You guys finished chapter 8, right? No. Can't remember when it closed. Is it Sunday?
Yes.
Cool. The word about it no more, right? That's nice. Conversion when r is less than 1. That is to say that x is less than 1, which implies that r is equal to 1. The radius of convergence. Anyway, we talked about all that already. So just a reminder, with this idea here, takes a function that is continuous and turns it into a series that is discrete. So the first couple will just be using this idea for geometric. So find a power series for the function centered at C. That C will be -3, I guess. Right, so centered at -3 means that we're going to have this going on. And so we're centered at 3. This is the original. We're going to rewrite it. So think of it as going in reverse, starting with a function and trying to force it to look like the geometric. See how, right? This was look equal to this, which we can then go to the sum. Usually we had a summation and we're trying to get to here. So now we're taking, you're given a function. We're trying to get there. So
Okay, I am confused on how do you get the x minus 3 at the bottom? Like I know that you have c equals -3, so I'm assuming that is c, but that just part, that denominator is just throwing me off. If you could explain it a little bit better, maybe, or like explain it a little bit more in depth.
Yeah, so when they tell you centered at, they're gonna give you that number, the c. So you just plug that in. So I'm gonna be shifting by -c. So it's always gonna be x minus whatever that is.
Oh, okay, gotcha.
So this is -3, so it's gonna be x minus 3. So over here, just a regular -x centered
Yes.
at 0.
Okay.
But we're trying to make it look like this, or this one. So that's what we're trying to get to. Eventually, I need to get the number in front, right? So I'm gonna go ahead and put the 2 over here. That'll be x plus 3, right? Now I need to have a 1 here. So I'm going to factor a 2. If I factor a 2, that'll be 1 plus x plus 3 over 2, right? You agree? Which will then reduce this 4. So now I have 2 over 1 plus x plus 3 over 2. But I need it to be minus. So I'm going to do, we're just doing weird algebra. That's not what we're doing. Minus, minus. So make sure you haven't actually changed anything. So now we can jump to the sum. So this 2 is whatever. All right, I'm just gonna leave it out here for now. So it's gonna be from n equals 0 to infinity. So I'm rewriting this function as a series, geometric type. So it's gonna be negative x plus 3 over 2 to the n. Train of thought there. So basically we're trying to get it in this form, figure out what the r is, and that's going to go in here. That's all we're doing. Given a function, and all right, maybe I can set it up as a geometric. Does that make sense?
Why don't we just what do you get minus -3 to the bottom? How do you get that?
So whenever you start this, when they tell you centered, it has to be minus whatever they give you. X minus c. Remember in the other last section we talked about the power series centered at some c. So if it's centered at 2, you would put x minus 2. If it was 0, then you would just leave it alone. Not worry about it. So this has a specific c. So this will determine the interval of convergence. If they don't give you one, then you're just going to start with this, and you're going to try to make it look like this, which would be a lot easier if it's just a plus 2. Right? You just subtract the factor of 2 out.
So you're serving the -3 from the plus, right? Because you're doing all that.
Yeah, that's all I'm doing is plugging in the -3 there. So x minus that. So true, whenever, whatever they give you, just put X minus that.
No, okay.
to deal with the center.
Yeah, okay.
Hmm.
Can you make it a little bit bigger?
Oh, yeah, sorry, forgot about that. No, I thought I was maximized. Forgot. So they will ask about convergence and all that, but I just want to make sure you understand
Mhm.
the transformation, because we already talked about the convergence, so. We'll save time for the next section. Find a power series for the function centered at C. Okay, so centered at 0, so we don't do anything fancy, right? What is our A? Right, well, it's already in that form, isn't it? What is A?
4,
It's 4, right? R?
7x.
Yeah. So this should, H of X should simply be sum of 4 times 7x to the n. When it's already in that form, centered at 0, it's a lot easier. Right? You don't have to do that x minus. Let's do one more that is not centered at 0. Next one, just so we can get disturbed by algebra. All right. There we go. And then we'll move on to the harder section. Find a power series function centered at C. Okay, so this one probably sucks. So as soon as I see the C, I think, you know what? Do the minus thing. Adjust it. X minus a positive 2, minus 5. Now I'm going to want that number first, so I might as well just move it now. Right? I need a 1 here. So factor 1 from, or 5 from both. Okay. So let's rewrite that a little prettier. So I got a 6/5 on top, right? Times 1 plus 3/5 x minus 2. So what is my A? 6/5. What is the R? Well, it needs to be minus, right? For the formula. So we would have to do minus, minus, right? So R would be yeah. What? Think about that. I don't really want it to alternate.
Well, isn't that 5 supposed to be negative?
Oh yeah. Those are already negative. You're talking about this one, right?
Yeah, that one.
Yeah, so if factor negative. Oh yeah, that's what makes it a little easier. So this will become minus. So we got a minus already. So R will be 3/5 x minus 2. So f of x as a series will be a series n equals 0 to infinity of 3/5 times 6/5. Forgot about that. Times, shoot. I rewrite that. Okay, so that'll be negative here. Negative.
On the finished expression at the top, what's the number of the fraction over there? It's negative 5, parentheses 1, minus.
Okay.
Yeah.
Oh, it's 3/5. Negative 3/5 times x minus 2. So the questions will start off like this, just find the series and then they'll ask you, does the convergent average once you find it. Okay, so I'm gonna skip that step so we can move on to the next one. The new stuff is changing into a series. Is there any questions on the algebra or the formula? All right. You guys cool on this page? A new section. Taylor and Maclaurin series. So Maclaurin, I think, came up with the original, and then Taylor generalized it or centered at NEC. So that's why they always name both of them. So the form of a convergent power series is the title. So if F is represented by a power series which we'll call f of x equal to the sum of an times x minus c to the n for all x in interval I containing c. Then a sub n is equal to f to the nth derivative times of c, sorry, over n factorial. And f of x would be equal to f at c plus f prime at c times x minus c to the first power plus second derivative at c times x minus 2 squared all the way until the nth derivative. You know what? I'll write it over here. It's better. I'll rewrite this. So this is the pattern that you should see, right? 0, 1, 2, n factorial. 0 derivatives, 1 derivative, 2 derivative, 0 power, 1 power, 2 power, nth power. That's the pattern. So we're going to use this in a little bit. Give some more definitions though. All right. Taylor and Maclaurin series. So if a function f has derivatives of all orders at x equal to c, then the series f to the nth derivative at c over n factorial times x minus c to the n is called the Taylor series for f at c. If c is equal to 0, then it is a Maclaurin technique. All right, so if your function has derivatives of all orders, meaning you can keep taking them forever, right? Then you can create a Taylor series representation of your function. So just like in the last section, we use geometric series, right, to represent functions. Now this is a more general approach. This will work with almost any function as long as you can keep taking derivatives. If the function kind of fades out right away, then it's not going to work. For example, x cubed, you would not do Taylor. But sine functions, e to the x, square root functions, those rational expressions, most functions will stick around, so they can be represented. I'll wait a bit, let my hand rest. Okay. I don't know if I have enough space for this. Maybe. find the Taylor series. For the function f of x equals e to the negative 2x centered at 0. So it's technically a Maclaurin series, right? It's okay. I think he'll get mad if we call it something else. Haunted by mathematicians. All right, so it's the procedure, you have to take a bunch of derivatives and then find the pattern. Once you create that pattern, that's going to be Fn. And then you plug it into that formula up top. So this is a little difficult. So zero derivative. Oops. Zero derivative. First derivative. Second derivative. Triple derivative. Do you see the pattern? So if it's essentially, that's what for sure we gotta incorporate an alternating part. And we also see powers of 2, so we're gonna make sure we got a 2 to the n or something. So we're gonna do that in just a moment. So now I'm plugging in the 0. We're gonna get 1, right? First derivative will give us negative 2. Second derivative will give us 4. Third derivative at c will give us negative 8. So the formula try expanding it a few terms so you can see the pattern. Okay, so formula says that the first term will be the first derivative, and this is the first value, f of c, right? Remember, formula is f of c over 0 factorial. So that's going to be 1 over 1. Right? This will be negative 2 over 1 factorial x minus 0. So just go through it. So just do it. So first one will be 1. That's the Fn part. Times x minus 0 to the 0 over 0 factorial. Next one is minus, right? Minus. Or if you prefer, put the negative 2 up here, it's fine. X minus 0 to the first over 1 factorial. The next one is 4. X minus 0 squared over 2 factorial. So we're getting, keeps going forever. So what is the answer? What is the pattern that, let's first piece by piece, right? Don't do it all in your head. I'm not expecting it to be crazy. So let's do the alternating part. So this is the 0th term. what should be the negative 1 part? I'll do the hard part for you. All right, we're starting at 0. So 0 factorial, good. 1, cool. So this one's done. This takes care of the factorials. Now, how do I set up the alternating?
You multiply it by -2?
There will be
Yep.
a 2 for sure, but first let's do the minus. Yeah, -1 n, right? So when it's 0, positive. When it's 1, negative. When it's 2, it's a square, positive, right? So we're good. So now we have an x term with powers of 2. So we could do the 2 by itself, or we can combine it with the x. But notice how the x is going to get 0 power, 1 power, 2 power, right? So the first 2 has a 0 power, doesn't it? So 2 to the n at 0 gives me a 1. At 1 gives me a 2. At 2 gives me a 4, right? So then this makes it alternate. So now we're good. We're matching with the index. 0, 1, 2, 3. Now the x part. 0 power, 1 power, 2 power. That 0 doesn't really do anything. So, right. So this actually represents e to negative 2x. It's pretty cool, right? You make it a little prettier, but that's pretty much your answer. We combine the 2 and the x, right? You don't have to. So what you should do is take a few derivatives, 3 or 4 is good. Plug in the c that you're given and find the pattern. And then just plug them in, plug in the numbers and see what's happening. Okay. Does that make sense?
Where does all of these the Taylor series apply? In which application in engineering?
It applies whenever you need a function that needs to be, like, for example, if you have a continuous function and you want to solve it numerically using like computer programming, but let's say you have a really complex problem, you can represent that equation as something that you can code, and then the computer will solve it for you. So sometimes you need to represent the function as something that's easy to program. Like this guy, of course we won't go to infinity technically, but you can have the computer run iterations, huge numbers, until it gives you the actual value. So it can compute this type of stuff.
I see. That's cool.
It's really neat, but it's really as far as like real world application, I would say probably if you were doing like there's probably senior level stuff, like a senior engineer. It's used in numerical approaches to solve various types of differential equations. So, I mean, it's hard to explain since we haven't got there yet. But there's techniques, like, let's say you work for, like, I don't know, Toyota or something, and there's this high level problem. And there's a numerical technique that you can use, but it'll take time to program. So at that point, it becomes great. But most of the time, that type of problem would be for someone who's been doing it a long time, you know, because it's a really complex approach.
I see.
It's called the finite element method. That method is only used when you have to because it's complicated and takes forever to set up. So like you have a really complex problem in your manufacturing or whatever, setting that up takes time, money, and knowledge. So it's great, but it's kind of like a very powerful tool, but only use it when you need to.
I see. I see.
All about resources, right? And time. You guys cool on this page?
Yeah, everything cool.
All right. Let's do. Let's expand the sign function. So given sign, can you expand it into a series? Okay. So I'm going to do sign centered at pi over 2. It's the same thing. Do a bunch of derivatives. So 0 derivative is just the same. Right. First derivative. What's the first derivative of sign? What's the
Negative
second
cosine.
derivative? Sine. First one is cosine. Next one is
Negative sign.
negative. Yeah. Third.
Negative cosine.
Yep. Let's go ahead and do 4. Fourth derivative.
And sine.
Do you see this pattern? What happened? It is repeating for sure, but notice how it alternates every 2. Kind of weird, right? We may have to deal with that. All right. F of pi over 2 sine of pi over 2 is 1, right? F prime at pi over 2 is cosine of pi over 2, which is 0. Double prime. Triple. It's going to be 0, right? Last one will be 1, 0, negative 1, 0, 1. Then it starts to repeat forever, right? At pi over 2. Okay. So that means the next one would be, right, we did the 5th. pi over 2, that would be 0, right? And then the 6 would be -1, yeah. And then 0, and then 1 again. So it looks like every odd is 0, right? So we can think of so we can skip the odd ones. Then we can focus on 1, -1, 1, -1, right? A natural alternating thing, not a skipping alternating. That's a lot harder to deal with. So let's just create a few terms and see what's going on. Let's create I don't know, 6 of them, so you can see it. So you can see the pattern repeat. Okay, so here's the formula. So the first one is 1, right? Times x minus pi over 2, centered at C, to the 0 over 0 factorial, plus 0 times x minus pi over 2, to the first 1 factorial, plus -1 x minus pi over 2 squared over 2 factorial, plus 0. I'm going to go ahead and write it over here. Plus 0 over 3 factorial over x minus pi over 2 cubed plus 1 over x minus pi over 2 to the 4th plus 0, right, for the 5th one? Yeah. So I'm hoping you can see the pattern better this way. Okay. So I made 6 terms so you can see it. So notice how all the odd ones are going to 0, right? So if I ignore the odd ones, I'm alternating 1, -1, 1, -1. Only the evens though. So all right, sorry about that. So let's deal with the alternating p's first. Okay, so notice that we're keeping 2, 4, 6 factorial. Right? How do you deal with that? The negative alternating parts right there. How do you deal with the 0, 2, 4, 6? How do you make it skip the odds? Like I need it to be 0, 2, 4. Because the n is going to be going through 0, 1, 2, 3, 4, right? That's what the series is going to do. So how do I force this index to skip odds?
Is it 2n?
Yeah, 2n. You see it? When it's 0, 0. When it's 1, I jump to here. When it's 2, 4, 3, 6. That makes sense? Okay, so we took care of the bottom part. Now, how do I deal with this? I don't want the ones, right? I want 0, 2, 4, 6. So same type of deal. So how do I write this last piece?
X minus pi over 2 to the 2n power.
Yeah. 2n power. You see how this will give me a 0, a 2, 4, 6 as this cycles through 0 to. So sine centered at pi over 2 will be represented by this guy. Any questions on this example? What's that? Yeah. Hope so. When you get to the homework, let me give you some pro tips. Evens use 2 to the n. Odds only use 2n plus 5. So this will give you odds, this gives you evens. If you want to be doing plus, minus, use this guy. If you want to start with a negative, plus, negative, use this one. See what I mean? If you wanted to do weirdness, like plus, minus, plus, minus, plus, we could have used this. So if this sign was not, if the sign was centered at 0, these would have stayed, right? So we would have to have used this guy, n times n plus 1 over 2 power. So that's a little tricky to, see in your head. So. And if you wanted to go the other way, let's say you wanted to start with plus plus, minus minus, plus plus, minus minus, plus plus, minus minus. You would use -1 to the n times n minus 1 over 2. But remember, this applies to any function. So sometimes the functions are annoying. Like let's say it's a hard derivative and you gotta do that derivative 5 times. So just be very careful. I recommend not multiplying anything out so you can see the pattern. Like I made a mistake. I guess not a mistake. On the last one, those are a bunch of 2s. I should have left it as just a 2 times 2 times 2. That way you would have seen the pattern easier. So try not to multiply stuff out. It's a rule of thumb. And yeah, just try not to leave everything factored. That'll help you see the pattern. But that's pretty much it for 910. Let me see what the. Maybe I do. I guess I haven't thrown the homework in there yet. But yeah, we're pretty much done now. Getting close, right? I'm gonna put the 9.6 in there. One second. So we can take a look at the homework. All right, so I'll start off pretty, similar to the first example, right? So except this one will be centered at 0, so it'll be a little bit easier. Take about 3 or 4 derivatives so you can see the pattern, plug in the 0, and then expand it a little bit and create your f. Okay, this one will alternate. This one will be a little bit similar to the last example. 4 would be a little harder. 5 and 6 would be annoying because it's a rational. So just keep it in parentheses as you do the derivatives. Because it's going to be x to the -1, right? And the first derivative will make it -2, -3, -4, right? So keep it in that negative form so you can see it. But I'm sure you guys are not near 910 yet. We'll worry about that later. Your future selves problem.